Hello there, physics. When last we left, we were talking about that stuff down there. Acceleration, how I don't like deceleration. Um, so scalars, vectors, we did the examples, acceleration versus deceleration. We talked, y'all had more examples. If I kind of give my, oh, no, don't draw over that. I just want to make a squiggle. There we go. So I'm just making a little separation for myself. Kind of like BC, right? So today was D-Day. We talked about graphing. So let's just do a quick recap of that graphing because I wanted to talk about another kind of graphing. I believe that the graph I did in class, I'm kind of looking at it, which is weird, because I'm looking up. Anyway, I believe that I had a graph that looked something like this. It went up, it went over, it came down. That's fairly dramatic. 1, 2, 3, 4, 5, 6, 7. Should be even more dramatic. Well, I guess it's as dramatic. 1, 2, 3. I labeled, we had that this was position, and this was time. And I guess I can pinch this in a bit. We don't need that to be nearly that big. So our x-axis represents time, y-axis represents position, or distance, from an origin. Now, this is not a perfect drawing, but it'll do for right now. We talked during class about how, let me put the numbers on here. Let's call this 3, let's call this 6, that would make this 7. Let's call this 1, 2, 3. Right. And then there was a little bit more, but let me just talk about this first. I labeled each part. I labeled this A, I labeled this B, I labeled this C. So this position time graph tells us literally, and I'll zoom in a bit so it's easier to see, literally where is our object and how long is it there. So our object begins at the origin. So it starts at, you know, if it were on a track, it would be the starting line. So start right on the starting line. It takes 3 seconds to walk 3 meters forwards. It's positive. And then for 3 seconds, they just stand there. They're hanging out. 1, 2, 3. And then in 1 second, they go 3 meters back. So, woof. All right. Now, I can tell that this is forwards moving because x is getting more positive. I can tell that this is not moving because x is staying still, right? The value for x is not moving. And I can tell that this is negative, this is going backwards, because x is getting more negative. All right, so the motion graph, this displacement graph, tells me literally where is the object and when is it there. From this graph, we also talked about how people said it was fairly clear that C was faster than A. Right? Line segment C happens in a shorter time period, but it's the same amount of distance covered. So they must be moving faster, whatever this is moving faster at C than it is at A. That makes sense. If I were to do the velocity, right, the velocity equation, which was velocity is distance over time, and I should actually, let me label this, let me be appropriate. This is D for distance. So if I did change in distance, which was 3 meters over 3 seconds, so velocity at A, right, is 3 meters over 3 seconds, which is 1 meter per second. If I did the velocity for C, which would still be distance over time, it's negative 3 meters in 3 seconds. No, it's not. It's negative 3 meters in 1 second. That means it's negative 3 meters per second. Now, if I were to look at these numbers, this tells me it's going 1 meter per second, this tells me it's going 3 meters per second. So C is in fact faster than A, not just from the visual of like lots of distance, little time, but also by the math. The math also helps because it gives us a direction. It doesn't just give us speed, how fast, it gives us a direction. It doesn't look like it, but I'm going to draw the direction for this one. It's positive, it's in the positive direction, which we would consider forward. This one happens in the negative direction, considered backwards. So those directional words, right? North, south, east, west, forwards, backwards, up, down, left, right. Those are directional words. Mathematically, we can use number signs. We can use positive or negative as actual directions. That can tell us direction. It allows us to be a little more generic. It allows us to kind of say, well, it's in the positive direction. We don't have to specify that it's up or to the right or forwards. It's just in the positive direction. Whatever we're calling the positive direction. All right? Now, this is nice. There's another type of graph that you should know about. It's very similar. It's a velocity time graph. Now, I'm going to draw how a velocity time graph, I think I need to zoom out just a tiny bit more. There we go. I'm going to show you how a velocity time graph and a displacement time graph, really this is displacement, right? So displacement time graph and velocity time graph can show us the same information, right? So I'll make the little hash marks. 1, 2, 3, 4, 5, 6, 7. 2, 3, 1, 2, 3. So for 3 seconds, then I have 6 seconds and 7 seconds. This would be 1, 2, 3, -1, -2, and -3. Try to remember that velocity is both a speed and a direction. So I could be going 2 meters per second, but if I wanted to make it a velocity, I would have to go 2 meters per second forwards. That would be +2. Or I could go 2 meters per second backwards, and numerically, on a graph, mathematically, that would be -2. So, for the first section, we said that it was +1 meters per second. So that would be, right, and you know what? I can do this. So, we're here. We are going 1 meter per second for 3 seconds. Then, for 3 seconds, we are still, which means that for 3 seconds, from 3 seconds to 6 seconds, we are right on the x-axis. Think about that for a second. The x-axis is 0. So it only makes sense that for that time period, we have a velocity of 0. We are not moving. And we said for the final leg, for c, our velocity was -3 meters per second. Oh goodness, what happened? Why is my taskbar here? There we go. We are at -3 meters per second. So we jump all the way down here. I want you to notice this is disconnected. You might see some kind of dashed lines, just to make sure that you know this is all one thing happening. But the velocity is 1 meter per second, then 0 meters per second, then -3 meters per second. This velocity time graph tells me exactly the same information about the motion of this object as this displacement time graph. There's exactly one thing that this velocity time graph does not tell me. It does not tell me where the object started. It only tells me how fast is the object moving at a certain time. Right? Okay. Now, there is one more thing that we'll talk about on your E-Day. I'll post those notes again, obviously, when we get there. But please make sure that you kind of recognize and you internalize this. You can view information as words. You can view information, usually you have like word problems, right? Now you might have graph problems where you have to graph something yourself. You have to interpret something from a graph. Typically it will be a combination of words and the graph. Base your answers on the information and the graph below. But know that you can find information about the object by looking at maybe just the shape, right, of the graph. You can also tell information by doing calculations from the graph. Now, I've rambled on a little long. We're rolling past 10 minutes here. I won't take too much of your time. But please, 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 try to recognize that there are going to be connections between the displacement time graph and the velocity time graph. They can show the same information even though they don't show it in the same way. Alright? More on that on E-Day. In the meantime, take care, y'all. Be good.